We are just after, since we are just after noon here in the Eastern time zone, I will get us started. Thank you to everyone who is with us already and joining as we speak for this roundtable discussion. And basically, the idea behind these roundtable discussions is an opportunity to talk more within our community, particularly in this case about the role of regional hurricane simulations as a core tool that we're trying to advance through a number of fronts. And I'm Tracy Kijewski-Correa. I'm going to be your facilitator or host for this event on behalf of the SimCenter. So just to give you a rough idea of what we hope to accomplish today through the design of this program, we want to, first of all, promote learning about the different hurricane regional simulation initiatives that are taking place, both as part of larger funded efforts and groups, or even on the part of individual researchers who are trying to advance one or more components of the traditional loss modeling workflow. The goal with these presentations, though, is not to dump and give you a standard presentation, is to give you a flavor of what our colleagues are working on, but then to give them a chance to highlight some areas where we have opportunities to advance the state of the art or challenges that they see we need to kind of collectively come together around. So each of their lightning talks, which will be approximately 5 minutes, will close with some questions or thoughts to provoke more conversation. And then we will open into a conversation with all of the attendees. And that's to achieve our third objective, which is really to foster some greater dialogue across people who are working in this space that is devoted to one or more elements of what would be necessary to conduct an end-to-end hurricane regional simulation. So our agenda for today, we're going to move through this brief welcome and introductions, and then I'm going to slide us into each of the segments. We've organized our speakers. We have 7 speakers, and they're organized around 3 segments. Each segment will have the lightning talks followed by a discussion block. And then if our timing is excellent and we're all well behaved in how much time we spend presenting and discussing, we'll even have some more time at the end for a broader discussion with our attendees. Now, to help you understand as an attendee how to participate in this conversation, you should see at the bottom of your Zoom screen 3 icons, which are your roadmap or way to engage with us today. The first you'll see is the first I want to draw to your attention is the Q&A icon. It looks like a double, talking box from like comic books, little bubble. That double bubble that says Q&A, that's where you can enter a question. And then once you type in a question, you can send it. And if these questions pop up in real time during any of the lightning talks, feel free to just put them in there and I will moderate those. You can use what's called the upvoting feature. So if you open the Q&A panel, you'll be able to see the questions and be able to upvote them to elevate them to my attention if you think it's a really good question. And you can also choose when you submit to do so anonymously, if that's your preference. The second option, of course, is the one we're all used to in the Zoom world, and that is dropping comments in or throwing in some questions or ideas in the chat for just real-time discussion among the attendees. So that's another venue, but I would say that if you have a question that you want the presenters to engage, I really would encourage you to use the Q&A button because it's the easiest way to curate those and move through those. And then finally, you also would have the opportunity when we enter in these discussion blocks, as I'm moving through the Q&As, if you want to jump in and further expand the conversation, just use your raise hand feature, which is the other button that you'll see on your display, the little hand, and then that will help me to call upon you. To help me with that particular aspect, please make sure that your name is displaying properly on your picture in the Zoom screen. You should be able to look across the little strip with all the pictures and see yourself. If for any reason your name doesn't appear correctly, let's say it shows up as user or iPhone, you can simply click the ellipsis, which is the 3 dots that you should see on your thumbnail image, and a menu will pop up that will give you a choice to rename. And if you do that rename, you'll be able to put a more correct or full name, something that I could call upon should you raise your hand. And we will unmute you at the appropriate time so that you can then engage with our colleagues in the discussion. So with those kind of orientations and ground rules, I want to get us started with our first segment. Segment 1 presents 2 researchers who are working to advance different components of this hurricane regional risk assessment workflow. The first is Tang Wu, who is a civil engineering professor at University of Buffalo. His research includes includes simulation of hurricane hazards and their impacts on coastal communities using high fidelity analytical and machine learning knowledge enhancing capabilities. And next, after him, we'll have Seymour Spence. Seymour is an associate professor at University of Michigan, specializing in AI-generated structural engineering. And some of his recent contributions are in the area of frameworks that combine 3D building, modeling, CFD, and AI techniques to estimate damage, providing high fidelity and individualized risk assessments, again, looking at hurricanes. So I am going to hand it over to Tang to begin sharing screen and take over with his lightning talk.
Okay, thanks, Tracy. Can you see my screen?
Yes, we can.
Okay. Hello, everyone. My name is Teng Wu, professor at the University of Buffalo. I'm in a conference, so I apologize if there is any background noise and music. But today I would like to share like some of our research team do like the title is AI empowered hurricane engineering. So we know hurricane is the activity is changing because of the climate change, and the hurricane caused all kinds of hazards like a wind, surge, wave, rain, flood, and those kind of hazards will kind of impact our community, like transportation infrastructure, tall building, all those things. So what we are going to do is that if we want to quantify the hurricane impact on the climate change scenarios, to do that, we develop a climate-dependent stochastic simulation framework for hurricane activity. So we call it BARC. And so the idea is that we can generate thousands of scenarios on the different climate scenarios and to generate the hazard field like wind, surge wave, and the rain. So the hurricane track model, probably many like folks like they are familiar with, but once you get the hurricane track, how to get the high resolution hazard field, like say wind field. So to achieve that goal, we develop like an AI-based hurricane wind simulation. So when hurricane is approaching, we know the hurricane like storm parameters input. We know the output is the wind speed. In the input output, you can use the machine learning. But the thing is that we don't have that many data. So to reduce the required data, we integrate what kind of knowledge. For example, the governing equation. So once you train the AI model, it's very efficient to give you the wind field. So once you have the wind field, you need to get the wind load, right, to estimate the wind impact on, let's say, on the facade. So we develop an AI-based wind load simulation tool. It's kind of end-to-end peaks, like this is motivated from the car industry. So if you have a kind of any change of your shape, they can immediately get the wind load, the pressure on the surface. So we developed this kind of knowledge enhanced CNN, which means you give me a picture of your structure, we'll give you the pressure, wind load, the pressure field, the things. And the domain knowledge we integrate including our Stokes equations. So that's the individual structure. And of course, we can extend it to the community. But for the community, like even you use knowledge enhanced CNN, you still need the data. Maybe data is not that many data, but you still need the data. So to generate data, we use the multi-scale simulation based on the WRF and ELES. Here, ELES is embedded LES, which is a very good tool in our practice. So similar things, we can do the AI for hurricane surge save, and then we generate the data and we train the AI model and then we can get a kind of a real-time prediction of the wave and the surge. And once we get the wave, we can also use the AI-based hydrodynamic load simulation, and we train the model. We can get the, for example, wave impact on our deck and scour things. But scour, we didn't get the AI model because we don't have that many data yet. It's very time consuming to generate data. Similar thing for the hurricane rain, we can also simulate the data, use the AI models to get the efficient rapid estimation of the hurricane rain simulation. Once we get the rain field, and what we are interested in is about the flooding. This kind of like inland flooding, we also use the AI flood simulation, and with the rain field input, we can get the inundation depth and the flood speed of the study area. So all those things, essentially, we are using AI and the knowledge. The knowledge including the domain knowledge, for example, the governing equation, the empirical equation, all those things. So essentially, we think that knowledge-enhanced machine learning is a very good tool to facilitate the simulation, but still we have a couple of challenges for the hurricane simulation. We have a high fidelity model, that's the regional scale. We also have at the structure scale, we also have a high fidelity model. But those high fidelity model, their challenge is the efficiency is low and the accuracy still need further improved. For example, we cannot do a very good physical parameterization in the mesoscale model, and some localized wind in the hurricane, we cannot simulate it really. And also at the structure scale, the turbulence modeling is always a challenge for people. And then we develop a low fidelity model or faster model. Faster model, the challenge is the accuracy is low, and the more efficient is needed developed. For example, we don't have like wind-driven rain, wind-borne debris, those kind of faster model. So, and also we have a Terra incorporata things. If we want to couple the mesoscale and the microscale, there are some issue there. So we think like maybe the multiple fidelity knowledge enhanced AI can help to facilitate this high fidelity, high efficiency simulation of hurricane hazards. I think that's pretty much all. Thanks.
Thank you, Tang. If you could unshare and we'll let Seymour go next, and then we'll open up for questions and discussion.
Okay, yeah.
Okay, so let me screen here. Okay, so can everyone hear me? See my slides?
Yes.
Okay, great. So thanks everyone for being here, and thank you, Tracy, for inviting me to give a couple of insights on some of those things we've been doing. So I think Tang did a nice job introducing kind of the overall framework. So what I'm going to talk a little bit about is use of AI and CFD and high fidelity vulnerability modeling, which actually interestingly is driven by hurricane models, similar to what Tang was actually discussing previously. So the sort of background on the work I'm going to be discussing here, which we've been doing in our lab, is how we know that a significant amount of damage within hurricanes actually occurs in residential buildings. Those are the buildings where you're getting a lot of impact. And if you really want to try and estimate that damage with any type of, I don't like to use the word accuracy, but with any type of, let's say, accuracy, one needs to be able to model and capture these mechanisms that are causing the damage, and these are generally associated with dynamic stochastic local pressures on the components, as well as windborne debris, which presents a whole host of difficulties to estimate and to model. So our kind of goal with this work was to reduce this kind of loss through data and AI-driven high-fidelity computational modeling. So the kind of workflows we were working on really had three components, actually more precisely four components. But if we look at this, we're basically saying that you should be able to use data-driven models to be able to create very high-fidelity representations of the components within your community. And when I say components, I'm talking about natural, man-made infrastructure and everything in between. We need to kind of capture all of that. And we want to do that using data-driven approaches. We can then create these digital representations of these realities and pass them on to our models for estimating the actual wind inside these communities. So here we're kind of suggesting using things like large eddy simulation, where we're capturing not only the kind of pressures on our components, but also all the local winds, as well as what's happening in terms of natural infrastructure as well. This also gives us this kind of outputs in terms of things like peak pressures on our various components for all of our buildings within our community, or infrastructure components in our community, which we can feed into physics-driven or physics-informed vulnerability models. In these types of models, we are explicitly capturing the progressive nature of damage as the event passes by. We're using the evolution of the event, or the description of the evolution of the event, from hurricane models, in fact, parametric hurricane models, but they can be more sophisticated if we so desire, as well as capturing windborne debris explicitly inside the simulation. Now, one of the things we were looking at here is acknowledging how, if you want to create metrics based on this type of simulation, which has any type of credibility, you do need to explicitly acknowledge uncertainty in your estimates. So you're going to have to propagate uncertainty. So you're going to have to couch these kind of approaches, these model flows, in some type of efficient means to propagate uncertainty. Here, efficient is really important. These are low probability events, small failure probabilities, and you don't want to run these models that much. You're going to have to be able to estimate this with a small number of model runs. So this is just a quick illustration of what we're talking about. So we're taking a lot of data, any sort of data we can get our hands on, really, to describe in detail what's going on within our community and all of its particularities in terms of morphology, its components, etc. And that turns into a digital representation of your kind of community. That includes everything from your built and your natural infrastructure, including things like the differences and the roughnesses of the surfaces, etc. We can then create sort of mesh-friendly versions of these digital representations. You can pass them directly to your, let's say, computational fluid dynamics models. You can run those using, for example, LES. And here you can use any type of reduced order models to speed up these types of computations. You can use AI-based technologies, machine learning, CNNs to, again, speed up getting these predictions from LES, as well as stochastic models that actually allow you to run multiple simulations, which are actually informed by only one or two real model runs. And what this gives you basically is this information about the evolution of the local effects of your wind field on your built and your natural infrastructure. Very high fidelity representation of these demands. So that gives you kind of your demands on all these infrastructure components. But one other aspect one has to look at is each one of these infrastructure components, if you're looking, for example, at residential buildings, not all of those components have the same susceptibility to damage. So you need this kind of representation or a way of identifying which components inside very large, extensive areas are actually vulnerable to a wind and then are going to fail first. So here we were kind of leveraging the Braille software, which is tools are available in the SimCenter, to try and identify the vulnerable components in these large communities. This is an AI-based technique which uses image recognition to try and go ahead and identify which components on each one of these kind of buildings and infrastructure inside your community are vulnerable. You can then associate suites of fragility functions to each one of these components and then run the simulations. We were using Braille. This was a little ways back. I would say that this technology here is a really great start, but it still needs a lot of work to really make it robust. It's a really interesting concept, but at the moment it still requires quite a lot of human input, which we'd like to get rid of. So once you have this kind of representation of your community and the damageable components and this high fidelity representation of your national and man-made infrastructure, you can then feed that into your physics-based or physics-informed vulnerability models and estimate damage as well as the evolution of damage. So we are looking at the progressive nature of wind damage, trying to capture that. But you do need, as we said, to propagate uncertainty. In particular, if you're looking, for example, at hurricanes, you don't really want to be just using simple methods for propagating uncertainty, because you're just going to generate a lot of events that are really not particularly severe. So what we ended up kind of doing here was using what we call stratified sampling. These are a bunch of stochastic simulation schemes, variance reduction schemes that we've introduced over the past few years, which really allows us to stratify the input space of uncertainties, identify where the most important events are occurring based on entropy, then sample right that. So we're, for example, getting all the simulations in those categories of storms where we're actually seeing most of the damage. In a certain sense, you get really large storms, you begin to have knowledge that you're basically going to lose your complete component. So you're really, well, you're going to have significant damage. You're going to wipe out the community. So you're interested in the division between the initiation and then extreme damage. So once you do that, what do you get from these types of simulations? Here we're just looking at a little collection of 8 buildings just to illustrate this. You end up with this kind of very detailed, fine-grained information on the damage to the individual buildings and the components inside your community. So here we're looking at these 8 buildings. In the middle plot there, what you see is exceedance probabilities of damage. This is damage state 2, which was moderate damage. So you're seeing kind of 15% of your roof cover is going to, you're going to lose, you're going to have window door failures, etc. So what we have are those black dots, which are kind of a classic vulnerability modeling approach, which you can see is pretty insensitive to which building you're looking at. Then you have those kind of red circles, which are coming from this type of simulation that we're discussing here. And you can see you get far more variation. So you're really seeing the effects of this localized damage and you're capturing it. And you can do this, for example, because we're doing explicit modeling of debris here, you can start to see the breakdown between damage coming from wind pressure and debris, and actually the local effects, how they change these ratios. So here, if you look at buildings B6, B8, what's interesting is you can see that, for example, where they're located in the communities, meaning that they're basically only getting damage from debris. While in other buildings, you're getting it all from wind pressure. So you get this information on where all this damage is actually coming from. Okay, so I kind of wanted to pose a few questions here, which we can then discuss later on. One of them is really how high fidelity do we really need or want to go? I think there is also this discussion between what the fidelity in your flood and your wind modeling is. This is a question which is coming up quite often in the work we are doing. And then the role of wind-driven rain, exactly where do we want to get into when it comes to simulating wind-driven rain? We've got some very sophisticated models for modeling that. I'm not sure exactly where that fits into these types of workflows. And then we've got some opportunities here, which I think are related to things like high performance computing, which is becoming more and more accessible. The AI, we've already leveraging it. I think we're going to be leveraging that more and more as we move forward because of how much more robust that is becoming. I think validation through experimental field data is really, we got unprecedented possibilities in that realm right now, which lends credibility to our models. And also it provides us the confidence in the predictions we're getting. And then uncertainty quantification. There's so many schemes out there which allow us to do this much more explicitly than I think we often end up doing. So is that, I have concluded, so I'm going to stop sharing my screen, correct?
Perfect. Yes, that would be great. And what I'll do is I will move instead to share mine, and that will let me set up our next speakers, because I think in the interest of time, we'll move into the next segment. No questions were posed, and so we may end up just sliding into a broader discussion with our attendees at the end of all the presentations. We'll sort of see how that goes with the attendees and how that flows. But let me take us into introducing our next segment. Segment 2 was designed to bring in some of the more kind of notable, if you will, efforts that are out there. So we invited INCOR to present, and Kushan Amini is a PhD student at Rice, who will be representing INCOR for us. He particularly is leading the Galveston testbed. And so we hope to learn more about those efforts today and what the INCOR team has taken away from their modeling efforts. In the middle panel, you'll see John Paul Pinelli and Kurt Gurley. And they're representing the Florida Public Hurricane Loss Model. John Paul is at Florida Institute of Technology, or Florida Tech, and he helps to lead that modeling effort, which is quite significant in the state of Florida, advancing much of the work he's done on disaster risk management and risk modeling over his storied career. And Kurt Gurley is flanking him again as a co in this effort and one of the collaborators and co-leaders of this effort. He is at the University of Florida, where he also helps to lead the experimental facility there, the Neri Wind Hazard Experimental Facility, as the associate director. And then we have Rachel Davidson representing the CHEER project, which stands for Coastal Hazards, Equity, Economic Prosperity, and Resilience. This is one of the Coastlines and Peoples projects. It's one of the larger ones of its type. And Rachel is a professor and core faculty member of the Disaster Research Center at the University of Delaware. So she'll be sharing with us some more about CHEER. And as you can see, I'm in the wind here myself. So I'm going to be stopping to share screen as we're in a windy day, and unfortunately got kicked out of where I was doing this meeting originally by a DJ because it is a football weekend. So I'm going to pass that over to Kushan to get us started from INCOR side.
Thank you so much for the introduction. Do you have my screen right now?
I do.
Okay, great. So my name is Kushan Amini. I am a third-year PhD student at Rice University, working with Dr. Jamie Paget and focusing on INCOR. So INCOR is part of the efforts from the SimCenter for Risk-Based Community Resilience Planning, which aims to develop measurement science to support community resilience assessment. This measurement science is implemented on a platform called INCOR, which, as you can see, stands for Interdependent Network Community Resilience Modeling Environment. On INCOR, users can run a scientific analysis that model the impacts of natural hazards and the resilience of communities to these impacts. And when we refer to communities, we encompass not only the physical elements like buildings and infrastructures, but also the economic and social dimensions that shape them. In this presentation, I will focus on Galveston testbed, where I am helping to lead efforts alongside Dr. Jamie Paget and others. In fact, I will use Galveston testbed to showcase some of the capabilities of INCOR platform. And as you can see, Galveston Island is located in the southeast part of Texas along the Gulf Coast area and susceptible to storm events, which makes it a good choice as a testbed for such analysis. To run the analysis, we first need to define the hazard and the built environment. As you can see here, we are using a coupled version of ATSIRC and SWAN to get the intensity measures, and all the results that I will show today is for a 100-year hurricane. We also have different inventories publicly available for everyone to use, such as building inventory and power and transportation networks. This flowchart shows the current framework we are working on. Everything starts with defining the hazard scenario and built environment inventories, as I mentioned. Then we have exposure models, which evaluates building damage and also damages happening to the different infrastructures. And after that, we are considering initial impacts. Here, we are using some data from the region, socioeconomic data, along with models like a computable general equilibrium CG model that gives us the economic loss and population dislocation model. And after that, we get to the recovery phase where we evaluate the housing recovery and different infrastructures such as transportation and power recovery. As you can see, we can evaluate different metrics and objectives. One of them, for example, could be economic loss, and we are working on optimizing based on the limited budget and constraints that we might have to find the most optimized solution and mitigation strategies so we can modify our built environment with different actions such as elevating the buildings, retrofitting buildings and different components and infrastructures, with the limited budgets to find and to make our communities more resilient to such hazards. As you can see, we are coupling both social and physical systems, as well as incorporating recovery over time. Here are just some of the results for Galveston Island and for the scenario that we have considered. On the first plot, you can see the damage states of different buildings after the hurricane scenario, and here are some of the failure probabilities for transportation components and power infrastructure components. And after that, we can find out if people have been dislocated from their buildings and what is the reasons behind that, whether it was building damage or inaccessibility to different infrastructures. And finally, we can estimate with INCOR when people get access back to power or mainland through the transportation network. As I mentioned before, we are also looking at solutions as part of the ongoing work in this testbed, like mitigation strategies and optimizing those solutions based on the budget and some other constraints. Encore is an open source platform allowing you to try all of these yourselves, like running simulations and see how the results change under different conditions. So please go ahead and scan these QR codes. You can have access. On the left, we have Jupyter book for Galveston, which you can go through all the Python codes and notebooks available for this testbed and run the whole simulations. And if you don't want to do the Python coding and use the codes, you can go to the Galveston app, which are set up the playbooks being available for run the same simulations and get the results. And by changing the conditions, you can see how the results would be different. To wrap up the presentation, here are some of the challenges and opportunities ahead. First of all, multi-hazard probabilistic assessment of hurricanes and their impacts on communities. We are addressing the issue of concurrent or sequential load effects from multiple hazards, such as wind, flooding, and storm surge occurring together during hurricanes, but we do not have multi-hazard models like damage fragilities for all the systems, that's for sure. We know how the second part is that interdependencies among infrastructure and other socioeconomic systems and the complexity of modeling recovery processes. So, you know how complexity and interdependent community systems can be, but capturing them all together remains a significant challenge and an opportunity, of course, for future work. Additionally, everything becomes even more complex when considering the recovery process, which adds further challenges to this analysis. And for the last opportunities and challenge, we are considering opportunities for leveraging machine learning and artificial intelligence to enhance models and integrate diverse data sources. So we are certainly looking to leverage AI to gather more information and develop better models and more reliable models. I believe this is a great opportunity for research across various fields of study right now. And at the end, I should also acknowledge the entire testbed and NIST team who work on this platform, as I am representing their collective efforts. Thank you so much for listening, and I would be happy to answer any questions you might have later. I'm gonna stop sharing now.
That's super helpful. And check the chat. I dropped a little note to you that I think would help our audience. With that cue, let me bring up our colleagues. I believe Jean-Paul will be presenting for us. So JP, take it away. You look great. Go for it.
Unmute, Jean-Paul. You're muted. Okay, can you hear me now? Yeah. So thank you for inviting us to this roundtable and to share about the Florida public model. Kurt and I, we've been partner in crime in this project for more than 20 years now. And this is a project that's been funded by the Florida Office of Insurance Regulation. So the focus is on insurance losses. It's been repeatedly accepted by the Florida Commission on Hurricane Loss Projection Methodologies. And as far as we know, it's probably the only CAT model developed in academia, which is actually used by the insurance industry and the insurance regulators. So like any CAT model, the FPHNM is a suite of models where we have a model for exposure, a model for hazard, a model for vulnerability, and a model for actuarial. And Kurt and I concentrate on the exposure and vulnerability models. In terms of exposure inventories, we cover single-family homes, manufactured homes, low-rise buildings, and mid-high-rise buildings. So we have a wide spectrum of buildings that cover what we call personal and commercial residential buildings. We have different vulnerability models for the case of combined wind and rain, the model at the heart of the model, we have Monte Carlo simulations which are based on a component approach, which mimic the physics of exterior and interior damage. And basically, we start with as input with a random wind speed from which we get a random estimate of the wind-driven rain, which translates into random loads and random impinging waters on the buildings, which are then that results in exterior and interior and contents damage. And the damage is estimated by comparing the loads and the amount of water versus the component capacities and the water absorption capacities of the interior and content components. So from that, we're going to get physical damage, which is then translating into monetary damage, and which then results in vulnerability matrices and curves. So we have 4 such models for the case of wind and rain for the different types of exposures. And recent advances in that area include the development of a component-based approach for interior and content damage modeling. I think we are probably one of the few models here where we look at the interior and content approach from a physics-based approach. We also develop a process-based approach for time-related expenses. And finally, we are looking at different hazards. So we just went through the certification process for our storm surge and waves and inland flood models, and we have a tree hazard model which is in progress. So we've published extensively. I'll encourage you to look at our papers if you want to learn more about that. And in terms of research opportunities and so on, wow, there are many of them in all the different areas, which obviously are going to overlap to what the other presenters already mentioned. So for example, in terms of hazard models, we are focusing our attention now on convective storms, climate change, sea level rise, and as I mentioned, tree hazard. In terms of exposure model, the question is always, well, what kind of exposure do we have? Where is it? How was it built? And so AI and machine learning can be a big help there. The impact of climate change and population shifts on the future exposure is a theme of potential research. And we can use these models that were developed for insurance purposes. We can add, and we intend to add a social component, social metrics to the models. Vulnerability models, there is a need to better understand the interaction between the rain and the structure, especially in the case of mid-high-rise buildings. How does the water propagate in a building and produce interior and content damage? New mitigation measures can be investigated. In the actuarial model itself, we can look at the cost effectiveness of these different mitigation strategies, the impact of insurance discounts, tax incentives, and we can try, look at all these issues in the context of different scenarios for climate change and sea level rise. Multi-hazard modeling is a big issue, right? In the case of wind and water, which one comes first? Which part of the damage is due to wind or versus water? What's the sequence of damage in the case of multi-hazards, and what are the different ways of combining these multi-hazards? And finally, uncertainty quantification is obviously at the center of these models. What are the sources of uncertainty? How does it propagate? And as we know, these are moving targets because we have change at every turn of the road in these models. So hopefully we can talk about that. So with that, I'm going to stop sharing.
Thank you, JP. I'm going to invite Rachel to share over as our last speaker in this second segment.
Okay, thank you. This has been wonderful. So I'm going to talk about the Cheer Hub, as Tracy said. The Cheer Hub is focused on the tension among these three major challenges: resilience to coastal hazards, economic prosperity, and equity within the dynamic context of climate change. And really, we started from a realization that all of this amazing knowledge and advances that have been made over the last decades still to a large extent aren't being reflected in the built environment and in the real world as much as they could be. And so our focus really is to try to help facilitate policy development, policies that are likely to be implemented. And the way we try to do that is to date, we've mostly tried to estimate losses and figure out what would be best for a community, and then convince the various stakeholders to do what we think they should do. And that doesn't work terribly well. People do what they want to do. So instead, what we're trying to do is understand how these different stakeholders, households, insurers, government agencies naturally make decisions, and then develop policies that align with that natural decision making, and also understand how the policies create outcomes for each of those stakeholders differently, so that we could find win-win solutions. And I should say that SimCenter is one of our partners, so we're very happy to be working with SimCenter on this. But with that in mind, the Cheer Hub is sort of centered on developing this framework, which we call STAR. And you'll notice the green boxes. So this is a computational framework with a bunch of interacting mathematical models. The ones on the bottom, the green ones, are what is we've been hearing about already today, that is sort of in a standard regional loss estimation. But what's different here is that we've linked it with interacting models of the way that each of these different stakeholders make decisions. So there's a big emphasis on understanding this decision-making process and how it links with our understanding of the risk. So when we combine all this together, we can get as results estimates, predictions about recommendations about what the government policies should be to achieve their objectives, and then a description of the decisions that we believe insurers and households are likely to make in response. Second, then provide the outcomes for each stakeholder based on what their roles are. And then by aggregating all the individual stakeholder results, we can get overall estimates of community resilience and equity and economic growth. So that just gives you the big context. So this loss modeling is one part of it. And as a result, it's quite a bit simpler than some of what we've already seen, although I'm really excited about what we've seen. So essentially, we have the hazards analysis, the building inventory, and then a loss model for the individual buildings that are combined to create, the maps of losses for each hurricane scenario. I should say we're focusing on housing, or the residential sector. We also, I'll add, that hasn't been mentioned before, is that especially when we're thinking about insurers and communities, we want to start thinking about scenarios in terms of a timeline of hurricanes, because when they occur in rapid succession, you get very different outcomes than when they're spread out over time. But the current status, I should say, it was originally developed 10 plus years ago, and we borrowed heavily from the Florida model that was just described, but in its earlier state. I know that the Florida model has evolved quite a bit as well and improved a lot. But in the current state, we're only representing wind and coastal flooding, single family wood frame homes. We were quite focused on, because of the relationship with the decision makers, representing retrofits. So describing retrofits as changes in building resistance from one level to another. and it's currently just working in North Carolina in Python. So with the Cheer project, which started more recently, we're trying to use this as an opportunity to really update and get with the times, I guess, on some of this modeling. So these are some of the areas we're focused on, and I would be delighted to try to talk with some of the previous speakers and see how we can leverage some of what's already been done. But we have some partners who are working on incorporating inland flooding and climate change, and applying it in Texas, which is one of our other state case studies. With relation to the inventory, we're working on projecting the inventory changes over time, which is, I think, something we need to start doing in loss modeling, because that's having at least as big of an effect as climate change, I think. Trying to just improve the loss models using some of the methods mentioned earlier, image processing and AI to get better description of the inventory and move towards building specific inventory. Another dimension I think that comes out of the focus of this work is creating a synthetic population and linking it with our households so that we have a tight relationship between the housing and the people who live in it, which will be important for community level losses and stuff. We're trying to the extent possible, kind of validate some of the loss model results with insurance claims data and the damage data from STEER, expanding to include mobile manufactured homes and multifamily homes and other types, and then importantly also looking at other loss metrics that are important to households. So these are being integrated into that STAR framework piece by piece. And so I like all the other research needs and opportunities and questions that have been posed before me. These are a little bit more specific, but I do think, like in particular, contents and non-structural loss, John Paul mentioned that. I think that remains a big challenge, integrating the flood and wind damage within single buildings, and then also incorporating the community scale mitigation into a same type of model. So we could start to look at trade-offs between that type of thing, like levies and nature-based solutions compared to building specific interventions. And I also want to mention, I notice on the call, there's a few of my collaborators on here, so you can direct questions to them. ET is here, Shanja Dong, and Sarah DeYoung, and I might have missed other people, but thank you so much for the opportunity.
Thanks, Rachel. And I just dropped the URL she had in the QR code into the chat for folks who want to check out more on Cheer. And with that quick segue, let me just share my screen one more time to introduce our last segment, and then we will open up to discussion with the remaining time that we have before us. So here is the intro to our last speakers of this segment. So we have David Ruch, and David is going to be representing STEER. We've been talking about data, so this is a great time to dive in. He's an associate professor at Auburn and is one of our associate directors in the STEER network, and he's going to bring some of that experience from post-disaster reconnaissance can help to inform damage modeling. And particularly, I think that will be helpful to tie a bow on a lot of the gaps we're all trying to close. And then Barbaros is joining us from the SimCenter. He'll be actually representing some of the tools that we're developing. He's worked a lot to advance our AI supported flows, including things like Braille's, one of the things you've heard today, and our tool R2D that brings together a lot of this amazing work to conduct these end-to-end loss assessments. So I'm going to let them take over for this last segment. And David, I'm going to stop sharing my screen so you can assume.
All right, sounds good. Thanks, Tracy. Do this real quick. And there we go. All right, well, as Tracy mentioned, a few of the presenters already have mentioned the importance of validation. And so happy to have an opportunity here to talk a little bit about STEER and producing some of those data sets that hopefully can be used as validation. And then at the end, I'll mention a few other initiatives that my own research group is working on that's related to some of this data. So to start with, if you're not familiar with STEER, again, the Structural Extreme Events Reconnaissance Network, this is just a network of researchers, practitioners. Our mission statement is building resilience through reconnaissance. So that really has two roles. One is actually going out and doing damage assessments or performance assessments in a structured and standardized way. But then secondly is also just trying to build the capacity of the community to be able to do collect perishable data that will be informative and helpful for the various research efforts that we're all engaged in. So it was formed in 2018 and formally established in 2020 and includes a diversity of storms that I'll talk about here in just a second. And of course is within many EERs within the NSF NARI Converge node. So just briefly mention and introduce my other partners here with STEER. Of course, Tracy is our fearless leader and director, and then you see the other hazard leads and research associates there. And then, of course, we're very appreciative of our wonderful advisory boards as well, several of those that are represented here on this call as well. And then thrilled to have, I don't know if we've crossed the 400 member threshold yet, but quite a few members from all around the world that are invested in the same mission that we are all a part of. And even as we speak, actively looking at the impacts of Hurricane Helene and judging our response to that. But this recent hurricane is actually a good transition into just introducing our tiered response model, because every event is different. Everyone has a different learning potential associated with it. And so our response is going to be tiered to the learning that we expect to be able to gain from it. And so you can see here, we have 3 different levels that we formalize our response into. And these are associated with either our virtual assessment structural teams that we call the VAST, or our structural teams, the field assessment structural teams. And so in a level 1 response where maybe it's a major event with some potential to generate new knowledge, it may just be a VAST that's just combing social media and other public data sources and then issuing a preliminary virtual reconnaissance report. And up on Design Safe, there's about 9, I believe if I counted correctly, we've had 9 of these thus far officially within STEER. But as the potential for new knowledge and evidence of the ability to generate that new knowledge from an event increases, we begin to respond with field teams, perhaps a scout team prioritizing street view imaging and drones to just rapidly canvass different areas and then produce a curated data set and a early access reconnaissance report. Or in the most extreme events where there are very clear knowledge gaps that we can address with the data, we'll send out Fast 2, which may be multiple rounds of teams coming in focusing on hazard characterization or structural assessments, and then of course the curated data sets from those as well. So in mentioning that though, let me just sort of highlight a few of the data sets that have been captured. And these are at various stages, as you hopefully would appreciate if you tried to do any of this yourself or use these. There's a ton of work that goes into taking unstructured, raw street view imagery or UAS imagery, or even the performance assessments, and then turning those into structured data sets. So these are at various stages of publication, but you can see there 11, and then I just realized that I left off Hurricane Maria, so there really should be 12 represented where we've had teams on the ground collecting information, whether it be performance assessments or driving vehicles through and collecting the surface level panoramas or street view imagery, high water marks, etc. So these are all either on Design Safe or in the works moving to Design Safe. If the Associate Director of Data Standards at STEER, myself, would get his act together and get them all up there as quickly as possible. But we are working hard on getting everything there. And if there's any data sets that you don't see on Design Safe that you're really interested in, please do reach out to me and we can get you access to some of the raw or the early data as well. But as part of that, as we're starting to look at all this data we're collecting from different storms, the idea is, can we move towards a data-driven regional simulation techniques? How useful can this be? And so as a first step towards that, we've recently published a paper where we've had a unified test bed across 5 different hurricanes and 5 different tornadoes. Right now, just focused on single-family residential buildings. That includes the 5 hurricanes listed there. But we're trying to standardize across all of those, the location and physical address and basic building attributes, estimated hazard intensities, the design or the basic wind speed, and then component level damage percentages. And then recognizing that that is just a start to the features that we would need and some better validation and predictions. Lots of efforts are ongoing to expand that feature set, both in breadth, including additional storms, and in depth, for example, including more aerodynamic features of these structures. So that's been published in a recent paper and on Design Safe. And the idea is this is a starting point that we can continue to build on that hopefully would be a great validation data set for all the interesting work that many of you are doing here. But as an extension of that really quickly here, also working on methods for blending the physics and the data together, because I mentioned 5,000 or so structures. That sounds like a lot in terms of data-driven methods with the amount of uncertainties that are present and the complexity of the wind damage relationship. That's not a lot of data. And so one of the things that a couple of my students are working on is sort of integrating these together. So for example, taking the SimCenter fragilities and then synthetic storms and creating synthetic test beds that we can use then Bayesian updating to link with the WISP or with our field data to then generate some causal graphs for rapid inference and prediction and inference of the relationships that are, some of them are known from Davenport wind loading chain and sort of our standard methodologies, and others are more nuanced, and this integration can help us understand them better. And then lastly here, one particular area that my research group is really interested in is on the resistance itself. So many have mentioned, for example, light wood frame structures. And in a lot of the regional simulation models that are out there right now, it's really sort of glossed over as a couple of arch types and a couple of options of component resistances. But as we've looked at the typical load paths doing detailed forensic studies, there are lots of sort of connections within the connection that have a significant impact on what the resistance of that vertical and lateral load path is. And so as we start to break it down and sort of capture all of these all these connections and the uncertainties associated with them and how that affects the overall performance of the load path, we can get a wide variety of resistances by a simple thing as just switching from a 1-inch round washer to a 3-inch square washer makes a huge impact in the overall resistance. And so how do we capture that? How do we look at capture that in our field data and then be able to model that appropriately in our regional simulations. And so I'll leave this here just since that's recorded. These are a couple of recent papers on it. And then in terms of the research needs, I can leave this here, Tracy, or if we're going to come back to these. But in particular, I think these overlap with some of the others that have been mentioned already. How to do non-structural performance, capture that within STEER at scale is something we've been struggling with for a little while. And then I'll highlight here the bottom left what I was talking about, and I think Seymour mentioned it as well, is sort of how much fidelity do we need? Is it okay to just sort of lump it in, just increase the COVs a little bit and to include some of these finer details, or do we really want to break it down and try to understand what's a true aleatory uncertainty versus an epistemic that we're okay with, or that we're just not including in the model yet? So with that, I'll just leave that here.
Awesome. Thank you, David. I'm going to go ahead and let you stop sharing so Barbara can take over, and then we'll use the remaining time for discussion.
All right. Can you see this okay?
Yes, you can.
Perfect. All right. Well, thank you, Tracy. For my presentation for the next 5 minutes, I'll be mainly talking about some of the existing capabilities in SimCenter and some of the upcoming ones for obtaining asset inventories. And we're going to be particularly focusing on natural hazards applications with this presentation. So in this context, you're going to be hearing the name Brails and R2D quite a bit. I'll start with Brails. So Brails is an AI-supported tool that we've developed, started maybe a few years ago, and it's been growing since then. It basically takes a simple location input, such as the name of the city or town you want the building or transportation inventories for, And then it basically taps into a number of public data sets. In terms of buildings, it could be building footprints to automatically identify the locations of buildings in the region of interest. For transportation, it could be, the geometric features for the transportation systems. It could be road center lines, bridge location, tunnel locations, and so forth. And what Brails does is it basically, using that information, obtains the imagery available, public domain imagery available on our internet, and then runs them through a number of computer vision models to extract attributes of buildings and transportation systems. The outcome is a set of features that you would typically not be able to get in databases such as text assist data sets and so forth. So in that sense, it basically is a method to get some of the data that will be essential to estimating damage and loss, or calculating damage and loss predictions, and do it in an automated manner. Just to give you a sense of some of these attributes, here we're only looking at the ones that we're able to get from images. There's other attributes Rails is able to get, such as design wind speeds, flood zones, things like that. But this is just the gist of some of the attributes you can get just for buildings. To highlight a few, roof pitch information is something that's fairly difficult to get, in open data sets. You'll be able to predict it with Brails. Some other things will be like first floor height, roof type, and so forth for hurricane, damage and loss studies. These are some of the parameters that could be important affecting your damage and loss calculations. I always start with the catchy part, getting these attributes from images, but Brails also has automated ways of tapping into public data sets. In terms of footprints, it basically has pretty much all the reliable data sets that you would want, Microsoft footprint data set, OpenStreetMaps, USA structures, you name it, all of them are in there. They're obtained automatically. You just enter the location information and everything sort of gets pulled in. And for transportation, basically everything that's relevant to assets in the US that are already there as well. And it also allows pulling in custom data sets. Say you've harvested the tax assessor data set for the region that is of interest to you. Rails is able to basically pull that data in and use it as a baseline and then improve on attributes that would be maybe important for you in performing your analyses. It pulls public domain information, typically Google imagery or some other sources, but it also has the capability to pull data collected using rapid equipment. David mentioned Steer. Steer collects a lot of data. You can actually pull some of that data in to create inventories. And then another thing you can also do is you can perform basic damage detection from street level and aerial imagery with some of the models that are already available and some of the models that we've sort of developed using some of the latest AI technologies, such as vision language models. And in terms of some of the upcoming capabilities, Brails is already able to get a baseline, a basic level transportation inventory. We're going to take that one step further by tapping into image data for transportation systems to get detailed information such as free column heights, abutment types, 3D geometries of bridges and some other transportation infrastructure components. And then another thing that's actually coming pretty soon is we're in the process of pulling in some of the open data sets available for power systems, and we're going to hopefully enrich them using some of the image data available out there. What you're seeing on the left-hand side here is basically a vision language model run for a street in San Francisco. And then, it's able to capture a lot of the details for power systems. It's just going to be a matter of automating this process for power systems in specific. And I just wanted to give you a quick overview of what this looks like, the process of generating inventories with Brails. I'm going to speed this up just for the sake of time. This is actually the Brails widget in R2D. So you can actually use Brails, almost all of the capabilities that I mentioned through a graphical interface where you define a region. In this case, we've defined Berkeley, California, and then you basically, select from the drop downs, some of the data sets that you will be interested in using. For instance, for this specific, example, we're using FEMA USA structures for our footprint source. We're using national structure inventory as our baseline, and running through it, I'll just stop it right at the end right here. You can, select the attributes of interest to you, and then you can basically come to a window where you can run the AI models. It's all done through a graphical interface, so you don't need to do Python coding to be able to use some of these tools. So we were able to improve on some of the existing capabilities, but the challenges are still there, and we're still trying to sort of close the loop on some of the tasks, the natural hazards applications. One of them is despite our ability to capture some of the tricky attributes such as roof pitch or first floor elevation, it seems that characterizing all the attributes to the level of predicting losses using the conventional models it still requires some work. We've in the past tackled this using rule sets, but it's not a one fits all kind of solution. So I think this is an area that requires work, or at least some additional thought. We're trying to still figure out how to close that gap. And another thing is, we're able to capture inventories for transportation systems and power systems to a certain level of abstraction. But it's not very clear, at least in the state of the art, if there is a minimum set of attributes maybe that will be good to, predict what the impacts of hurricanes will be to these systems. So this is, I think, an area that requires some discussion. Certainly something that we've been thinking on quite a bit too. So those are a couple of challenges that I had identified, and particularly focusing on inventories. And I think it would be good to, spend some time talking about them. Thank you.
All right, thank you, Barbaros. And so what we have right now is approximately 20 minutes available to us for conversation and discussion. I know that our colleagues who presented had a number of areas that they provoked as, and some common threads that run between them. I wanted to actually start at the highest level because there were some questions in the Q&A that provoked whether or not and how we even intend to use these simulations that we're talking about. So one question, I think David posed it, how much fidelity do we really need? There's a lot of question about higher fidelity models and the values of them. But I'd love to hear the thoughts of the speakers about how much fidelity is enough and to what end. So maybe I'll start there. What's the limit on fidelity? All right, so we'll go David, and then I think Rachel jumping in after that.
Yeah, I think that's a great question, and also addresses the one you mentioned as far as who's the audience for these regional models. And I think that depends on how much fidelity you need. In the space that we've been very active in recently is more on the education side and sort of trying to promote active or actionable things that builders and homeowners and so on can do. I think you need high fidelity. You need to be able to give details of what caused, really how much benefit do we get from, again, my example of switching from a 3-inch square washer or from a, round 1-inch to a 3-inch square. Does that matter? So being able to show those cost benefits really takes some accuracy and fidelity to be able to communicate that effectively to that audience.
And then I think, Rachel, you want to jump in next?
Yeah, I was going to add, I think that's an important research question, but it really depends on how the models are being used. But I'll say for what we're doing, like when you start to try to distribute the loss to a house among the different people who are paying parts of it, the household, the insurer, that it does become really useful to have more high resolutions of, I think, the older models that were really more geared towards just getting an estimate of the total loss for the whole event. That doesn't need to be as high resolution, but I think we're asking these models to do a lot more than we used to. And so the high resolution, we could really take advantage of it.
Seymour, you want to jump in?
Yeah, so that's definitely, I think, an important question. In fact, it was one of the questions I actually posed as well. And why do we need high fidelity? My answer to that is ultimately we need people to take action, right? So in the end, how do you get communities to actually respond better, be more resilient? One of the key actors in this are the owners themselves. And most people own a house or they own some very limited part of that community. So if we have these very averaged models, which are very good at getting an average loss, it's very difficult to drill that down and give actionable items to individuals who can actually then make a difference to the overall resiliency of the system. So I think these high fidelity models, what they do is they provide much more detailed information, going back to what Rachel is saying as well. So you suddenly have a much better idea of what I can do to help me. And if every single person within the community has that information, we should get an overall increase in resiliency where, in a certain sense, we are moving the responsibility more onto the individual owners rather than focusing so much on trying to have these very large kind of mitigation plans, which are part of our kind of toolbox, but I think we need to get that information to the individuals who are most affected. It also, I think, would make them feel more empowered to actually do something about it.
I'm glad to see JP jumping in because from the cat world, I'd love to hear your thoughts on this.
Well, I was going to say it's a system question, right? Because if you have high fidelity in one part in the exposure, in this case, it's useless if you don't have the capability to make use of it in the other part. So by that, I mean, for example, in the case of an insurance model where you're going to treat portfolio with maybe hundreds of thousands of buildings, if the hazard model is not going to give you, for example, the orientation of the wind with respect to the building for each building, then you won't be able to take the whole advantage of high fidelity in terms of the model. And if you don't have a vulnerability model that takes advantage of all the details in a building, then you don't need them either, right? So I think that at least in insurance models, high fidelity might not be required, or at least it has to be at all levels so that you don't waste resources in one area that is useless because you cannot make use of it.
And this actually raises an interesting point that I'm going to try to pull the thread on some more because a lot of it, it's one question is whether we can get to the fidelity level we want and then being able to do that consistently across that entire loss modeling workflow. The second is you're dealing with a lot of uncertainty as you're moving through these different stages of the analysis as well. And there was a question from an anonymous participant that I want to use then to segue here. The question is, how feasible is it to get the level of information or data we need to actually get to higher fidelity? And you can pick which part of the loss modeling chain you want to think about, but do we have the data to get there, or what's stopping us? So I'll open that to speakers. Well, is it to get the data and information needed to get to that level of fidelity?
I mean, I can jump in here just on the resistance side since I spent a lot of time doing that. Can it be done? Yes. And hopefully if we do enough very detailed ones, then we'll see more of the, I guess, ways to develop surrogate models, if you will, that can establish better rule sets. But right now, and this is nothing new. You read back some of the early 90s, I think Henry Liu had some great papers on assessments and, emphasizing there that it's a lot of hard work. You got to dig through all these connections and find out exactly what the load path is. And if you want that fidelity, and that's not very fun work a lot of times. But we're trying to do some of that now. And then my hope is if we can do enough to then be able to establish some broader, surrogate models that then make it easier to sort of develop rule sets that apply more broadly.
I think Seymour was jumping on this.
Yeah, so I think one of the barriers to high fidelity previously was always computation, right? So you can make models higher fidelity and then you would just crash into a wall of computational impossibility. And those type of impossibilities are getting, the barriers getting lower and lower and lower. So we can process so much more data so much more efficiently now. AI makes this so much easier. So I think the barriers to doing this are much lower. I think we do have a lot of models that actually allow us to simulate at high fidelity. We have so much more data now. I think a very important point, I think Jean-Paul was bringing up, is that you need to make sure that your model chain is consistent. There's no point in having an extremely high fidelity model in one part and then have a huge amount of uncertainty in another part. So you've got to try and keep that model when you're developing these things even. But one way around that, which is important, is that one needs to capture explicitly uncertainty in the model chain itself, and then acknowledge in some parts you have less fidelities than you have in others. You'll always have that. And what you need to do is have these epistemic uncertainties, which captures that in your model chain. So as you get better, you're going to get higher and higher fidelity results that do capture uncertainty overall in your knowledge as well. But I do think we have these models. Computation is getting cheaper and cheaper. AI, surrogate models, all sorts of different methods for propagating uncertainty as well makes it much easier for us to do this. It just turns into a problem of actually getting the resources and getting those models together and then capturing all the data which is required for validation. These models do need validating. So what David was saying is really important. Having this type of work, looking at this stuff in detail, getting understanding in the uncertainties, limiting them, then actually makes one be able to make these predictions.
And I think I want to both applaud but echo, again, this all comes down to commitments to share that data, to systematize how we capture, to share it. And that includes down to the level of cities, right? Encouraging inventory data to be exposed and shared reduces reliance on a national structure inventory. That isn't exactly the best thing, but it's what we often have. So I was recently testifying at the Climate Solutions Caucus for the Senate. And that idea of sharing data, encouraging local data sharing at all levels, right? From municipalities up. And, making sure that, I think, as Rachel's often, echoed in some of her comments and other forums, that includes loss data, which is the one we share very infrequently. Data on our utilities and infrastructure, which often, again, are hidden away, especially when we talk about power infrastructure. So we can, I think, have these advances if we don't get that data sharing and all commit to it ourselves and encourage more of it. Teng, I know you wanted to jump in, so I'll let you add to this.
Yeah, I agree. I think the data is the critical, and also when we do the simulation, for example, we can do the multiple scale simulation. But when the data, even though individually they share the data, I guess we still need like a platform to how synchronize the data. For example, if we do, let's say, during hurricane, we want a high fidelity wind effects on an individual one building. And then let's say we want a time history of the pressure. We did that work. I mean, nowadays the computer, we use the several hundreds millions of cells. That's not a big issue. We can use the high performance computer. We simulated the hurricane, we simulated the pressure surrounding the building, but then how to validate that, right? And how many like the field measurement pressure data out there. And out of them, how many pressure data has been synchronized by the weather events so that we can compare. So that's very challenging, and I think is really deserve like a lot of like effort to synchronize all those information.
And Seymour, were you echoing back on that?
Yeah, I just wanted to echo quickly back on that because I think the SimCenter is doing a really great job like that. We've just done in one of our studies a validation on some of the high fidelity damage modeling we were getting, and just having that information on the type of buildings, type of damages you were getting, type of intensity of the event. It wasn't actually that difficult for us to get a pretty good validation on the final damage predictions we were actually making. So yeah, maybe we can't validate the wind speeds exactly. You can't validate maybe some of the kind of models within the chain, but because you get the outcome and you know what the event was, outcome in terms of damage, ultimately that's what we're trying to simulate with all these model chains. If we get really good validation on those results, we then begin to validate the overall model chain.
And I'll give a shout out for Hurricane Helene. Those of you who are not on Design Safe Slack, and there's a channel for Helene right now running. I posted it in the chat a bit earlier. This will be an event where we have pre-event LiDAR wave gauges out, sentinel towers. If you don't know what those are, they measure wind concurrent with the storm surge. And hopefully we're going to come back behind that with structural information, right? And what you're already seeing is sharing of some of the details of the inventory at the spots where these hazard characterizations are being, conducted and measured. And I think it's a beautiful example. If you go on that channel, it's about 100 people and they're sharing information. These are the kind of events where you can link each part of that chain because you're making observations at all of those. And those validation sets are going to be vital to us being able to recreate and ultimately see if we can get these models correct. Now, Rick had a very good question. I will shout out that INCOR has a simulation already posted there, a rapid simulation they did for the affected area that is on the Helene channel. I will put the Helene channel back into the chat again for those who might have missed that. But Rick asked a really important question, and his some of his data were used to feed into that simulation that INCOR ran overnight. The question was, do we really know the sensitivity analysis fundamentally, right? Do we have an understanding of the sensitivity of these downstream results to the fidelity of these individual elements, particularly upstream? Everybody wants to know this work on sensitivity. I know some of you have looked at this, and this is, as Jamie pointed in the chat, an evolving thing that we need to continue to work on, and directly feeds in this question of how much fidelity is needed. Anyone want to jump in on sensitivity analysis and what are the implications downstream of the fidelity of these elements, potentially upstream in the workflow or chain?
I'll jump in maybe and make one comment if I can, Tracy, that I think it's been explored perhaps more from like a systematic uncertainty quantification perspective, where we're looking at these classic sensitivity analyses of chained models where we have uncertain random variables defined, and maybe we can start to parse out how, if we do consider their variation, they influence the outcomes. But I think what we haven't explored well at all is there were so many decisions along the way, and picking and pairing those models through the chain, and how does some of those decisions also affect the outcomes? I think that's really underexplored. So I don't think that gives a solid answer, but what I do think, going back to the earlier group's conversation, is it certainly has to be a fit for purpose model chaining, right? If we care about just these global estimates of recovery trajectories at an aggregated scale, then maybe we won't see the benefits of some of those refined parameterized fragility models, for example, or heightened data collection at one scale. But there probably is another purpose, like individual owner retrofit decisions, where we could see the benefit if it doesn't get overshadowed by other models along the chain. So I think there's a lot to do there.
And I think, one of the things I want to elevate about what Jamie said is that when we then think about the data we need to capture, that sensitivity helps a ton, because otherwise you drown in the number of fields and information you're trying to gather to be able to give the supporting data that's needed. I know we felt that in STEER. By the time you throw the kitchen sink literally at all the things you need to collect, you drown the data collectors on the ground. So, we've been trying to work to figure out what are the core pieces of information. Maybe we don't need everything, that are actually most sensitive to then being able to produce a high quality data set that can validate some of these models and reproduce the vulnerabilities that are driving the losses. I'll open if anyone else wants to jump on the very important question Rick posed, but the one that's loaded all day long. All right, we've got some courageous people. Let's go. Mershad, I think you had your hand up, maybe?
Yeah, so I just want to add one point, that based on my experience, last month I was running a near real-time damage model for Hurricane Helene, and one of the decisions that I had to choose was making choice between existing damage model for flood, for building at the parcel level. And the option was looking at the hazards, for example, damage curves or more advanced fragility curve that is available. And that's going to be highlight the importance of sensitivity analysis, even at the end that I get the input from hazard layer, and there is no, so I didn't know which one to choose. And it's kind of, I want to highlight that. Thank you.
JP, you want to jump in?
Yeah, I was going to mention that there is limit anyway to the high fidelity that we can achieve because we can have high fidelity regarding exterior characteristic of a building, for example, but regarding the interior, that's basically impossible, right? Interior and contents losses, damage losses are the driving losses in for uh, 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 for low intensity hurricane, I mean, to category 1, 2, maybe even 3, and which is, a lot of the events. And so there is a lot of work to be done also on that aspect here. And how do we evaluate or validate interior and content losses?
And that perfectly hits the comment that's in the Q&A, one of the questions. That question says, can we even get there? It feels almost hopeless to chase after the high fidelity model if we can't get the inventory data needed at that level of detail. For example, a 3-inch washer. A lot of those details are hidden, right, within the construction of the building. And unless those things are exposed as part of inventory generation by the owner, the producer, the builder, or the municipality that does, the inspection, it's going to be hard to recover that from many of the visual tools we have. We simply can't see those things from the outside, JP, in addition to what was done along the way when that building was constructed. It's really difficult. Kurt, did you want to chime in?
Just along those same lines, the other aspect of validation when it comes to insurance data is the claims data that you could get from insurance companies. And that claims data, believe me, does not say we paid off $15,000. $5,000 was for the carpeting, $3,000 was for the exterior finish, $2,000 was from broken windows. That fidelity does not exist in claims data. So we might get every single component wrong and land on the right number by accident. So what good is the fidelity is a good question.
So I always leave it to you to leave me with such hope and optimism on a Friday. So I'm going to close with one question, and I don't know who wants to grab it in the interest of time, but you all concluded your slides with challenges and opportunities and questions that are burning inside of you. If you could answer those tonight with my magic wand on a Friday afternoon, what would success look like? What would your tool be able to do for our world? And we'll see who has the courage to grab what would success look like if we could magically solve all that's holding us back. How do you hope these models or these capabilities would change our world? Seymour jumping in. Uh-oh.
I'm going to jump in. I'm going to go for this. I will be really happy if we had a capability of telling individual owners what that actual risk and risk evolution is as they change and they make decisions. I really do believe that it's at the individual owner level where you can really make a change. And if you can get them inside the loop and they have the information necessary and they feel part of the process, that's where you can make a big change. And I think sometimes our models are just too far away from the individuals who don't even feel connected to them.
And I will say that was one of the messages I heard a lot in DC during my visit last week was we need more skin in the game. It's going to be an all hands approach if we're going to be able to reverse course on what we're seeing in terms of mounting hurricane losses, as Rachel said, sometimes in rapid succession. We've got a hurricane right now that just came ashore, in the wee hours here in our country. And continually our current mechanisms through insurance, FEMA, and the role of state and federal government is simply proving inadequate to both prevent the losses and even to effectively recover afterward. Maybe what we can do as modelers can reveal the right vulnerabilities, the sensitivity now show what matters most. But maybe, as Seymour said, our biggest obligation is to get as many hands on deck in trying to get ahead of these storms rather than chasing them from behind. So with that, I thank you for joining us here today in this roundtable. And I encourage you to stay engaged. This is a chance to bring us all together. If you want to continue to stay engaged with us at the SimCenter, I would encourage you and do a quick plug to come over to the SimCenter website. And you'll see that in particular, there is a subpage about how to be part of the community. I encourage you to jump into that community, whether it's joining our working groups, any of the discussions, and even things like these roundtables. So much good work going on. So proud and thankful for all the good colleagues who are trying to do their part to make sure we're not cleaning up every time a storm comes ashore. Thank you all. Have a great weekend.